This presentation is about tolerance stacks or stack-ups, and particularly about statistical tolerancing. Earlier presentations explained why you need TOLCAP for checking and setting the tolerances you put on drawings. If TOLCAP is good for individual tolerances, then hopefully you will see that TOLCAP is, well, essential for tolerances in combination in tolerance stacks. Statistical tolerancing is almost always misapplied. We'll have a look shortly at why statistical tolerancing is invoked and how it's usually applied with no consideration of any underlying assumptions. In fact, there's a general lack of awareness that there are any underlying assumptions. Tolerance stacks are not easy. The theory is essentially maths, and I apologise for that in advance. But the explanation will involve some maths, but it really isn't very advanced, and I will take it slowly. It's necessary to be able to explain the assumptions of statistical tolerancing, why TOLCAP is vital, we think, for valid statistical tolerancing, and to show a straightforward method of calculating a sound statistical stack tolerance using TOLCAP. First, let's look at what we mean by a tolerance stack or stack-up. We set tolerances for components, but it is often necessary to ensure the parts fit properly when they're assembled together. The diagram represents an assembly. Three, let's call them blocks, dimensioned D1 plus or minus T1, D2 plus or minus T2, and D3 plus or minus T3 are fitted side by side into a cradle dimensioned D4 plus or minus T4. Will they fit? Okay, this example looks unrealistically simple, and your real designs will be more complex, but often they do essentially reduce to this problem statement. Clearly, we need D4 to be somewhat greater than D1 plus D2 plus D3 to allow for the blocks being larger than nominal size. But if that somewhat is too large, the assembly may be too slack when the blocks are smaller than nominal. So what should we specify for D4? And what should be the tolerance on that dimension? Well, we always start with the worst case analysis, don't we? The assembly will always fit if the parts are in tolerance and if D4 minus T4 is greater than D1 plus T1 plus D2 plus T2 plus D3 plus T3. Or rearranging that and taking it to the limit where it will just work, D4 equals D1 plus D2 plus D3 plus T1 plus T2 plus T3 plus T4. Note we add T4, now it's on this side of the equation. More often than not, when the dimensions are at the opposite end of the tolerance band, the assembly would be unacceptably slack. When all the dimensions come out on nominal, the gap is the sum of the tolerances, and when D4 is at maximum tolerance and the blocks on minimum, the gap is twice the sum of the tolerances. At this point, someone will usually say, "Whoa, let's use statistical tolerancing." We don't have to add up the individual tolerances. Statistical tolerancing lets you root sum square them. What's that? Well, you square them all, add the squares up, and take the square root. So now D4 equals D1 plus D2 plus D3 plus the square root of T1 squared plus T2 squared plus T3 squared plus T4 squared. That tick means the square root of. And this gives a smaller answer for D4, so less slack. Hurrah! But is it justified? We know that root sum squaring numbers gives a smaller answer than just adding them up. Pythagoras knew that. We can see it's a shorter distance along the hypotenuse of a right-angled triangle than going round the other two sides. But does this have any relevance to the situation we're in here? The basis of statistical tolerancing is, as I said, a mathematical theorem. Suppose we were to make up a variable, let's call it stack, constructed by adding or subtracting a number of component variables that are all independent, and that means that the value of one of them is not in any way related to any of the others. Let's further suppose that the probability of finding a particular value for one of these component variables obeys a normal or Gaussian distribution. and the variable I has a mean x bar I and a standard deviation sigma I. Now, it's a property of the normal distribution that if you do add or subtract variables that are independent and normally distributed, as we want to do to make up this variable stack, then the result follows a normal distribution. Further, this variable stack will have a mean which is the sum of the component means and a standard deviation which is the root sum square of the component standard deviations. The means will have to be added algebraically, that means added or subtracted as appropriate, but the sigma squares are of course all positive, so they just add up. So that's the theory, and if we could travel forward in time, we could measure the dimensions of the components in the stack, assure ourselves they're indeed independent, check that they're normally distributed, and measure x bar and sigma, mean and standard deviation for each. Then we could properly calculate the stack tolerance. And if our tolerances happen to be the same multiple of the sigmas for each component, and if the x bars all come out at the nominal dimensions, then root sum squaring the tolerances will work fine. But how do we know? If we don't know, there's no justification for root sum squaring, and how could we know? Well, we have TOLCAP. If your head hurts, this might be a good point to pause this presentation, walk round the office before continuing. See you soon. Okay, if you're ready, we'll continue to use this same example to explore the traditional approach or approaches to statistical tolerancing, and then to look at a method for calculating stack tolerances using TOLCAP. We'll compare and explore how stack tolerance, which we'll call tstack, is calculated as a function of the component tolerances. So tstack equals a function of tolerances. For example, tstack equals the root sum square of the tolerances, square root of t1 squared plus t2 squared plus t3 squared plus t4 squared. We'll look at this and some others, but the algorithm or equation will be given and explained for the general case. But purely to compare approaches, we'll take a rather artificial case where all the component tolerances happen to come out equal. T1 equals T2 equals T3 equals T4 equals T, and then for that, let's call the stack tolerance T star stack. The following slides will use some maths, so let's review some recurring mathematical manipulation here first. As explained above, sigma di means add up all the values, and don't forget there may be plus or minus. So in our example, we were looking at dimensions, and to calculate the nominal gap in our stack, sigma di equals minus d1 minus d2 minus d3 plus d4. Remember that root uppercase sigma I squared means square all the standard deviation sigmas, add them all up, and take the square root of the sum. If there's a constant involved in one of our equations, we can usually take that out to make things simpler. So if we're trying to do the root sum of c sigma I squared, what we can do is take the sum of the sigma squareds and then multiply by the c squared afterwards, and then take the square root, or even more simply, just do root sum sigma squared and then multiply by the c. And that enables us to say, for example, that if we're doing design for 6 sigma and we set all our tolerances equal to 6 sigmas, then root sum sigma squared equals the root sum of t squared all divided by 6. Or even root sum of 4.5 sigma squared is root sum of the t squareds times 4.5 divided by 6. And finally, for the purpose of the comparative example, note that for 4 equal tolerances, T1 equals T2 equals T3 equals T4 equals T, if you add them up, sigma Ti is 4T, but if you root some of the squares, then you get just 2T. When statistical tolerancing was conceived, a tolerance of just 3 sigma was considered entirely adequate. Really? Well, Back in the day, a designer's education would start not with an engineering degree, but more likely with an apprenticeship in the factory where he was going to work. So he'd be reasonably familiar with the parts and what could be achieved. If not, he could always go down into the factory, have a look at a part with a dimension similar to the one he was considering and see if there was a control chart for it. Now, on a control chart, action limits are set plus or minus 3 sigma around the mean of the parts coming off the machine. So, if he matched his tolerances to the control chart limits, he would first of all be achieving CP equals 1, and he would get 99.9% of his parts within tolerance, which was considered okay, and he could quite justifiably root sum square his tolerances of his components for a stack tolerance. Now, this procedure was found to give an optimistic result, it's worth noting, and in 1962 Arthur Bender Jr. published a paper which proposed adding 50% margin to the stack tolerance. Now, that 50% margin is actually 1.5 sigma. And where have we heard that before? Well, it's the offset we set in Design for Six Sigma, which is worthy of note. Benderizing is still a mainline traditional approach. However, these days as designers, we're probably not quite as familiar with the parts we're designing as they used to be in days of old, and going to the factory may be difficult if the parts are being made offshore. But we have TOLCAP, and while TOLCAP predicts CPK rather than sigma, we can make use of TOLCAP to analyse, starting from the traditional method, and then look at how it can be developed and improved into a process for actually setting stack tolerances. I've mentioned the 1.5 sigma shift, so let's just see where that comes from. Design for Six Sigma says to set the tolerance to 6 sigma to allow 1.5 sigma for the process shift, i.e. for the mean in production not lining up with the nominal dimension. Does this mean that the process shift for every manufacturing process really is 1.5 sigma? No, of course not. There's no law of nature that would cause that. It's actually derived from the cunning of the manufacturing people. The shift should be less than 1.5 sigma, but if necessary, a shift any greater than that could easily be detected by a standard 4-sample X bar R control chart. A control chart can't be too commonly needed, so this implies that 1.5 sigma is generally more than sufficient. The process shift recognises that the mean dimension of the parts is not necessarily equal to the nominal dimension on the drawing. How does that come about? Thinking real process shifts, for some processes such as turning, the shift will depend on how well the setter has set up the machine for the batch. For processes such as moulding, the process shift will to a large extent drift over time as the tool wears. So the process shift thus includes at least an element which is not variable from part to part but fixed from batch to batch or drifts very slowly over time. So while it makes sense to root sum square the random part to part element of the tolerances, hoping they are independent and normal, it may be prudent to combine the process shifts worst case and simply add them up rather than root sum square them. The empirical data in TOLCAP reflects the reality of the various manufacturing processes. It confirms that 1.5 sigma is sufficient for the process shift, but not always necessary. The process shift in TOLCAP may be as much as 1.5 sigma, but it will be smaller if that's appropriate to the process. Now, extracting the process shift from the TOLCAP tolerance is no simple matter. It varies across the maps and the effects of the wizards. But let's use TOLCAP, taking the Six Sigma approach, to derive our stack tolerance. But we'll assume that the process shift in the tolerances is the full 1.5 sigma. We'll see that this gives a reasonably conservatively large estimate for the shift tolerance, and we can always do a sensitivity analysis later to see by how much we might have overestimated. So to derive a stack tolerancing algorithm, we'll get our component tolerances from TOLCAP. We'll use TOLCAP to find the tolerances we need to achieve a target process capability. We want sigma values for these tolerances. So as we said, we'll start with the Six Sigma approach and tolerances. So open TOLCAP, select a process and select the CPK tab rather than tolerance. Enter the nominal dimension, set the target CPK to 1.5, apply the wizards and find what tolerance TOLCAP gives. Repeat for each dimension in the stack. For each component tolerance obtained on this basis, we assume we have a 6 sigma tolerance so that the tolerance equals 6 sigma, but that's made up of two elements. The process shift, 1.5 sigma, is a quarter of the tolerance, and the part-to-part variation element is 4.5 sigma, which is 3/4 of the tolerance. We can't root sum square the process shift elements, we have to add them, but we can root sum square the part-to-part variation element. So the tolerance stack comes down to sum of the tolerances times a quarter plus 3/4 of the root sum square of the tolerances. In the specific comparison case we made, where all the tolerances are equal and equal to t, the stack tolerance comes to the sum of the tolerances is 40, we divide that by 4. The root sum square of the tolerances is 2t, we take 3/4 of that, add them together, and we end up with 2.5t. The stack tolerance is 2.5 times the component tolerance. So here is at last a method for finding a designed for Six Sigma stack tolerance. For each component, set the target CPK is 1.5 and thus find what we're calling 6 sigma tolerances from TOLCAP. Add 1/4 of the sum of the component tolerances to 3/4 of the root sum square of the tolerances. But of course the analysis above assumed that we would get a designed for 6 sigma 1.5 sigma process shift in the tolerances obtained from TOLCAP. If we knew the process shifts in TOLCAP were smaller, we'd have to modify our calculation. For example, suppose the data in TOLCAP reflected only 0.5 sigma process shifts for all the components of the stack. Then a CPK of 1.5 target tolerance will comprise 4.5 sigma still for the short-term part-to-part variation, plus only 0.5 sigma for the process shift. A 5 sigma tolerance where we expected a 6 sigma tolerance. What's the effect of this? Well, the process shift at 0.5 sigma must be the tolerance divided by 10, and the part-to-part 4.5 sigma variation must be represented by 9 times the tolerance over 10. So if you put that into our formula, tstack would come to 0.1 of the sum of the tolerances plus 0.9 of the root sum square of the tolerances. Then we can compare this with our case where all the tolerances are equal, and then tstack would come out to, when you've done the arithmetic, 2.2 times the component tolerance, and that's instead of the 2.5 times the tolerance we got where we assumed 1.5 sigma process shifts. Not a great error. In fact, we didn't know we had a 5 sigma tolerance, but we have some confidence that our computation assuming di is equal 6 sigma I is conservative, and the margin, as we say, is quite small in tstack, would be 12%. Let's take that to the limit. If there were processes such that all the component process shifts were 0, then each tolerance would be just 4.5 sigma, and we want to simply root sum square the tolerances. In this case, we'd find that the stack tolerance is pretty straightforwardly twice the component tolerance, and the margin in the tolerance stack from our original calculation would be 20%. But the assumption that none of the components requires any allowance in the tolerance for process shift looks unlikely in practice, so any overestimate in the algorithm looks acceptably small. But wait a minute, up until now I've been recommending that you design using TOLCAP's default CPK equals 1.33 tolerances. We'd better modify the algorithm for the stack tolerance. So for the same process and dimension and method as in the 6 sigma case, we will still assume the process shifts are 1.5 sigma, and for CPK equals 1.33, our tolerance needs another 4 sigma for part-to-part variation. So we're now apparently doing design for 5.5 sigma. So if the tolerance is 5.5 sigma, then 1.5 sigma must be 3/11ths of the tolerance, and 4 sigma 8/11ths of the tolerance. And then we work out our stack tolerance as before, but this time it's 3/11ths of the sum of the tolerances plus 8/11ths of the root sum square of the tolerances. So we have a simple algorithm for tolerance stacks with a minimum CPK equals 1.5 or CPK equals 1.33 to match our component CPK requirement. We hope this presentation has explained the assumptions of statistical tolerancing, why TOLCAP is practically essential for valid statistical tolerancing, and a straightforward method of calculating a sound statistical stack tolerance using TOLCAP. And this method is, for a 6 sigma tolerance, use TOLCAP to set component tolerances at CPK equals 1.5, and then the stack tolerance will be, let's say, 3/12ths of the sum of the tolerances plus 9/12ths of the root sum square of the tolerances. But for the TOLCAP default, CPK equals 1.33, use TOLCAP to set component tolerances at CPK equals 1.33, and then the stack tolerance will be 3/11ths of the sum of the tolerances plus 8/11ths of the root sum square of the tolerances. For more information, including our blog and other articles telling you how to get the best out of TOLCAP, do visit our website at www.tolcap.com. At the very least, do have a look at the last video in this series, which is a worked case study illustrating the ways of using TOLCAP that I've been talking about in these videos.